dear students, this is Sir S, and today I'm back with another exciting tutorial, and this one is for class 11 and belongs to the last chapter, that is waves and oscillations. And today's topic I'll be picking up with this Doppler effect in sound. Okay, the simple idea is like this. If this is a source of sound and this is the observer, or the observer, then say the sound wave produced by the source, let us say it is having a frequency nu, and when it is received by the observer, this will be getting a new frequency, nu just like this. It's something like you are listening to the whistle produced by an approaching train. Suppose here is a red roll track, and this is the train or a bus, something like this, and this is approaching towards you. You are standing here. What you find is that in the beginning, the sound of the vehicle or the whistle, let us say engine, or maybe a train, and if it is a train, let us say whistle. The whistle produced by the train in the beginning, when you observe it in the beginning, it is not that loud, but when the train comes closer and closer towards you, then what you find that the sound becomes more and more louder, and the loudness of the whistle is maximum when the train is very close to you, and if it is moving away from you, the loudness of the whistle goes on decreasing. Like, the simple thing is like this: sometimes you hear the sound louder, sometimes less loud, means that more faint, you can hear it all the time. The frequency of the sound keeps on changing all the time. So this change in the frequency of the sound due to the motion of the source, or you may be coming closer to the source also. So it means that there will be a change in the frequency whenever a source of the sound is approaching towards the observer, or the observer coming towards the source. So this change in the frequency due to the change in the position between the source and the observer, this is what we call as the Doppler effect in sound. So in a very simple way, you can write like this here. This is the change in frequency of sound whenever there is a change in the distance between the source and the observer. This is the case. Now let us keep on deriving one equation for this. Let's say this is the source S, maybe the whistle you're going to blow here, and let this be the observer. And just to apply the mathematical laws, let us join this with a line, and let us think that from the source the waves are coming here like this. Waves are coming towards the object, towards the observer. This is the observer here, and let us keep that let us think that these 2 points, the source and the observer, these are kept at a distance of v, let us say. And now I'm going to take another figure, the same figure. Here is the observer, and this time the source is moving closer towards the observer, and think that it is moving from S to as this. Now shifting now this point to shifting to as this. So this time the source will be appearing here. It means that the sound seems to be coming from here like this. Here. Now what you find when the source moves up to SDS, you can see there is a slight increase in the frequency. And this time let us think that this is approaching through a distance of, let us say, Vs here. That is from S to S, that's Vs. So this distance from here to that point should be, you can see here to here is V. From V you're going to subtract Vs, so the remaining should be V minus Vs. You have this. Now let us use the formula for the wavelength. The wavelength of the wave should be lambda should be equal to V by nu. This one is coming from the formula. Nu varies inversely with wavelength, and as you know, frequency is equal to what? C by lambda, where C is the speed of light. In our case, C, the speed of the light, is what replaced by speed of the wave here. V is the speed of the wave. Then what I mean to say is that this V is the original velocity or speed of the wave here. Then after approaching from S to SDS, you are going to have another wavelength, a new wavelength. Should be getting now. This should be equal to say this lambda dash. This is belonging for, or this lambda dash is what belonging to SDS here. So your wavelength now becomes lambda dash. This is equal to, for this, the distance, this V will be replaced by V minus Vs all divided by new frequency, the same frequency now. Therefore your new frequency we call as the apparent frequency. This will be given by our new frequency nu dash. This should be equal to the same velocity V we have and another wavelength lambda dash, let us say. And keep in mind, this is our new frequency. This is the new frequency. This is what you're going to find it out. And this new is the original frequency. So when you find a new frequency, you are going to have another new wavelength, and that is. So now this is equal to this V I read as before, V and lambda dash. This one I use this term here, V minus Vs divided by nu. So finally your new frequency, this is equal to V, this one multiply here, and what this is V minus Vs. You have this formula. And if you look here, if you look at this formula, here, this formula, say nu dash is equal to V nu divided by V minus Vs in this formula. Let us see. Compare now here in the figure. This V is greater than V minus Vs. So what we say is that this term, since this V is greater than V minus Vs, this is greater than this. So if it is greater, means if nu is greater, nu dash will be greater than nu. Nu dash will be greater than nu. What does it mean? It means that if this V, if V is greater than this one, means that if this is greater, these two are directly proportional. So if it is greater, nu dash should be greater than nu. It means that your new frequency, the new frequency also we call as what? Apparent frequency. This is greater than the original frequency here. This is greater than original frequency. This is possible if the source is coming closer towards the observer. Now, if the source of the sound is coming closer to the observer has a new frequency, new this. It means that if the source is producing a frequency nu, this is the frequency of the sound produced by the source, and this is the frequency of the sound heard by the observer. So the equation says that the frequency of the sound wave heard by the observer, this is greater than the original frequency. It means that the new frequency heard by the observer, this is greater than the original frequency. It means that the observer will be listening to the sound more louder. This is the case. So what you find, there is a change, or there is an increase in the frequency when the source is coming towards the observer. So this is what we call as the Doppler effect. And suppose say if this is the observer, and if it is observer here, and if the source is moving away, like a bus which is getting farther away from you, in this case you'll get the opposite case here. The frequency heard by the observer, this will be less than the actual frequency produced by the source here. It means what you're going to listen will be having lower frequency than the original one. It means that you will be hearing the sound more fainter if the source is moving away from the observer. Suppose say if a bus is moving away farther from you, the loudness of the sound goes on decreasing here. So this is all about the Doppler effect, and I hope that this will be useful for you. And if you have some more topic you want to know, you can request me that.